in this video, we're going to talk about some basic probability facts. We're going to compute some probabilities, usually from other probabilities, but we will also rely on your intuition a little for ones that hopefully you'll believe, because it's not until the next video where we finally figure out how to compute a probability in this class. So, just to remind you, a probability is a numerical measure of the likelihood that a specific event will occur. Now, the notation we're going to use is PR of E. I'm going to try to use that, but P of E is the same. So if you don't want the R there, I may or may not write it. I normally do write PR though, so I will try to do that to be consistent. But just note that these are the most common notations for the probability for an event E. So first we start with some basic notes about probability. So first of all, a probability for any event is always between 0 and 1. Okay, so this is something very important to remember. The probability for every event is between 0 and 1. So if I ask you a question for probability and you give me an answer that's negative or bigger than 1, I know immediately it's wrong. Okay, the probability for every event has to be between 0 and 1. Now, the higher the number, the more likely the event. Okay, so the closer you are to 1, okay, the more likely the event is to occur. Now, we talked about an impossible event in the last video. So if E is impossible, that means that it definitely cannot happen. In that case, the probability of E, so the likelihood that E happens, is 0. Okay, this is the minimum number. Okay, so probability 0 means cannot happen. Okay, so that event is not possible it's impossible. If you have a certain event, so that's when your event E contains every possible outcome, that means that it's definitely going to happen. So that means its probability is 1. Okay, so these ones definitely occur. Okay, so those are the extremes, and every other event is in between those two. Okay, so suppose we have a sample space with capital N elements. Okay, so I've just listed them, little s1, little s2, all the way to little sn. Okay, now an event with just a single element, okay, we call that an elementary event. So it only has one element. And then just some notation or lack of notation maybe. If we call PI the probability that the outcome SI occurs, then some notation that maybe if I didn't tell you, you might not even notice, okay, but PI is actually the probability of the event SI occurs. So this is the event, this is the elementary event. Okay, so the event with one outcome. Now, because I probably say this often, but because we're lazy, we sometimes abuse notation. So technically the probability is the likelihood that a specific event will occur. Okay, so not an outcome. But we use it sort of interchangeably, so you could write the probability of SI instead of having the curly brackets to indicate that it's a set. Okay, but you should still think of this as the event containing only that one outcome. Okay, even though there's no set braces. Okay, so that's just a small note on terminology or notation, actually. So one thing that we often use to sort of summarize the elementary probabilities, so the probabilities associated with elementary events, is the probability distribution table. Okay, so this is what it looks like. Now I drew it horizontally, it takes up less space that way. You could draw it vertically if you prefer, doesn't matter. The main points that it has is it has a row or column, okay, that contains all of the outcomes. Okay, so every possible outcome is in your table. So these are single outcomes. Okay, and then together with their associated probabilities. Okay, so basically it says the probability for each outcome, the probability that that single outcome occurs. Now, just a note here, what would happen if I added up all of these, oops, I used a capital N. If I added up all of these probabilities, okay, exactly one of them needs to occur. So the group of all of them should be the sample space. It should be a certain event. And each of these elementary events are mutually exclusive. So it turns out that if we add up all these probabilities, we should always get 1. Okay, so this is true for all probability distribution tables. So if you are making one and your probabilities don't add to 1, it means that you either made a mistake computing a probability or you're missing an outcome. Okay, so that can be a way to tell that you've done something incorrectly. Now let's construct one, very basic one. And again, I'm sort of relying on your intuition here for the probabilities, but I think that should be okay. So the experiment is where we roll a single die and record the result. Okay, so that's our experiment. So we want to have outcomes. Okay, so every possible outcome together with its probability. So the outcomes are the numbers 1 to 6, because those are the only things that we can roll using a 6-sided die. Okay, now when I write these probabilities, here's where I'm relying on your intuition. So hopefully you believe me that when we roll a die, the probability that I get a single number, so say number 1, is 1 out of 6. Okay, so each of these probabilities is going to be 1 out of 6. Okay, now again, if we add them all up, I have 1 over 6 plus 1 over 6 plus 1 over 6 6 times. I'm definitely going to add to 1. So I didn't break this condition up here that I said will always be true. But if you roll and it's a fair die, you should expect the probabilities to be evenly distributed. Okay, so hopefully that you believe that they all have chance 1 out of 6 of happening. Okay, so we also have the addition principle. So this is very similar to what I called, I think, the addition principle for counting. So suppose I have an event E. Now I've written it S1, S2 to Sk. It doesn't have to be the first K outcomes in your sample space. Okay, so it's just any K outcomes, okay, of S. Then if I want to compute the probability for E, what I can do is add the probabilities for each of these outcomes. So you're adding the probabilities for each of the elementary events. Okay, so using our other notation, this would be P1 plus P2 all the way to Pk. Okay, so that's the addition principle. So going back to that other example, suppose our event E is the event we roll an even number, okay, when we roll one die. So that means that E contains the outcomes 2, 4, and 6. Okay, so using this addition principle, the probability of E should be the probability of 2 plus the probability of 4 plus the probability of 6, which would be 1 over 6 plus 1 over 6 plus 1 over 6, 3 over 6, which is 1/2 if we reduce, or 0.5 if you prefer. Okay, now this hopefully makes sense. Half the numbers are even, half the numbers are odd on the dice. So hopefully it seems reasonable to you that the probability we get an even number is 1/2. Okay, so half the time we'll get an even number. Another thing we can use for probability that is the same, basically, as for counting, is the principle of inclusion-exclusion. So if E and F are events, then, and you want the probability of E union F, just like you could with the number of things, you can compute probability of E, add the probability of F, and then subtract the probability of E intersect F. Okay, so again, this is barely a new formula because this is exactly the same, but with PR replaced with N. Okay, so number of. Okay, it looks exactly the same. And again, we had that special case where if E and F were disjoint, or in this case, mutually exclusive, then when you want the probability of the union, you just have to add the probability of E and the probability of F. Okay, now that's because this last probability is going to be 0. Okay, since they're mutually exclusive means that E intersect F is empty. So the probability of E intersect F is 0. Okay, so there's no outcomes in the intersection, which means that it's an impossible event. Okay, let's try another example. So, suppose we have a bag of 12 marbles. The marbles are numbered from 1 to 12. The first 6 are yellow. Numbers 7 to 10 are green, and 11 and 12 are purple. Okay, we're going to select one marble from the bag, and we want the probability the marble is green or has an even number on it. Okay, and notice that it's the word or. Okay, so which means that you could think of having the statement or both at the end. So I'm going to call G the event that the selected marble is green. Okay, and let's call the event E that the selected marble has an even number. Okay, so what we're looking for is the probability that at least one of these happens. So we're looking for the probability of G union E. Okay, so using the pi, this should be the probability of G plus the probability of E minus the probability of G intersect E. So now we want to think about each one. So there's 12 marbles in total, and we're equally likely to grab any of these marbles. So how many of them are green? So numbers 7 to 10 are green. Okay, so that means that the number in G is going to be, so 7, 8, 9, 10. That's going to be 4. 4 of the marbles are green. There's going to be 6 of them that are even. Okay, so the number that are even is 6. So the number in E is 6. And the number in G intersect E, so how many of the green marbles are even? It's going to be the numbers 8 and 10. Okay, so there's going to be 2 of those. So we reach into the bag. 4 of them are green, 12 of them in total. So hopefully you believe me that the probability of G should be 4 out of 12. Okay, so 4 even ones, 12 in total. For E, probability we get an even number, 6 of them are even, 12 of them in total, so there's a 1/2 chance. And then if we get a green even marble, okay, there's only 2 of them out of 12 that we could grab. Okay, putting these together, we get 8 out of 12, which is the same as 2/3. Okay, so we would say the probability is 2/3, or that is 0.66, approximately, I guess, 0.667, if we use 3 decimal places. Okay, now again, I'm trusting your intuition here a bit. Okay, so G has the numbers 7, 8, 9, and 10. Okay, so that's where this 4 comes from. Okay, the 6, we have 2, 4, 6, 8, 10, and 12. Okay, so there's 6 of them we could grab out of the possible 12. And for this 2, it's just the 8 and the 10 that are green and even. Okay, so hopefully that makes sense. We're going to talk more later about how to count this for sure. So let's do another one. So suppose there's 2 events A and B of some experiment, and we know some stuff about the probabilities. So we know the probability of A is 0.4, the probability of B is 0.6, and the probability of A intersect B is 0.1. What if we wanted to determine the probability of these sets? So A complement intersect B and A intersect B complement. So one thing we can do is we can still use a Venn diagram to help us. So in this Venn diagram, we have 2 events. Okay, remember events are like sets. So I have event A and event B. Now here my universe, so the rectangle, is S. Okay, and what I'm going to put inside are probabilities. Okay, so the total probability is 1. Okay, so what that means is all spaces sum to 1. Okay, and then we fill it in the same way we did before. So start in the middle. So the probability we're in the middle of A and B is going to be 0.1. And now I know that the A circle, okay, the total A circle should add to 0.4. So this leftover space should be 0.4 minus 0.1, or 0.3. Okay, the total B circle adds to 0.6. So on this space here, I'm going to have 0.6 minus 0.1, or 0.5. And then on the outside, I'm going to have 1 minus all these other bits. Okay, so that's 1 minus 0.9, so I get 0.1 on the outside as well. So now it's easier to compute these probabilities. Okay, so A complement intersect B, we just have to go back to our Venn diagram knowledge. So you're not in A, and you're in B. Okay, so that's going to be this space here. And we just said that probability is 0.5. Okay, now if we wanted A intersect B complement, okay, that's, you're in A, but you're not in B, so that's this part of A over here. So this probability is going to be 0.3. Okay, so once you can still use the Venn diagram, and once you do, you can usually pick out where the probabilities are. Okay, now that I've sort of relied on your intuition a bit, I'm going to warn you that you need to be careful when you trust your intuition. So a paradox is a statement that's counter to many people's intuition, okay, but yet is actually true. And one of the most famous examples of this is called the birthday problem. So let's think about the problem here. What is the probability that at least 2 people in a room of 38 people have the same birthday? So that's month and day, but not necessarily year. Okay, so just the same birthday, not year. And here we're assuming birthdays are equally likely, which maybe isn't that valid of an assumption, but I think that birthdays are more likely to congregate around certain times of the year. So I think that we're actually doing an underestimate for this probability here. Okay, and we also assume the number of days is 365 per year. So if you're born on the leap year, I'm sorry, we never consider you. So we always are assuming 365 days. Now, at this moment, we don't actually know how to compute this probability. Okay, it's rather challenging to compute, but we can still think about how likely this might be. So there's 365 different days that you could have birthdays. There's only 38 people. So how likely is it that at least 2 of them have the same birthday? So in previous years in my classes, I've asked this, and I normally get guesses like 5%, so 0.05, or maybe 10%, so 0.1. It turns out, and the highest I think I've ever got is like 25%. Okay, but it turns out that this probability for 38 people is actually 0.864 approximately. Okay, so it's almost 87% likely that in a group of 38 people that at least 2 of them are going to share the same birthday. It's actually quite likely that this happens. Okay, so this probably is counter to your intuition, because there's lots of days in the year and there's not that many people. Why would they be likely to have birthdays that match? Okay, but it turns out that they're more likely to match than they are to not match. So the chances that everyone's different is actually quite small. So this is sort of counter to people's intuition. So we want to be careful, which is why in the next section we're going to talk about how to compute these probabilities in sort of a mathematical way. Okay, so we will be making assumptions, but hopefully they're reasonable assumptions. The last thing I want to talk about here is another way to express probability, which is called odds. Okay, so instead of giving the probability, you give the odds that the likelihood that it will happen. So you give it as a pair of integers, and it's like the chances in favor versus the chances against. So for example, when we roll a 6-sided die, what are the odds we roll a 2? Well, we would say the odds in favor of rolling a 2 are 1 to 5. Okay, maybe I'll write 1 to 5. So the 1 is the ways that it happens. Okay, and the 5 are the ways that it does not happen. Okay, so I could roll a 2. Okay, that's the only way that it happens. For it not to happen, I roll a 1, a 3, a 4, a 5, or a 6. There's 5 different ways to not roll a 1. So the odds are going to be 1 in 5, or 1 to 5. So, in general, when we say the odds in favor of event E occurring are A to B, what we expect is in A plus B trials, the event would occur A times. Okay, and fail. Not occur, fail to occur B times. Okay, so that's sort of what we're thinking. So if we want to go between odds and probability, so it's usually easier to go, I think anyway, from the odds to the probability. So if you have an event E and the odds are A to B in favor of E, then the probability of E is going to be A, so the number of ways that E should happen, divided by the total number of trials, which here is going to be A plus B, right? So we're in A plus B trials, we expect it A times. Okay, so that's where that probability comes from. Now, if you have the probability, so say you know the probability of E is P, then the odds in favor of E occurring are found by reducing the fraction P, I need a pen, okay, P over 1 minus P. So what you want to do is reduce this to lowest terms, okay? So if A over B is this fraction in lowest terms, then the odds in favor of E are A to B. So I wanted to just do a quick example of that so we can see how this works. So suppose event E has probability 0.4. What are the odds in favor of E occurring? So we would write 0.4 over 1 minus 0.4. So that's 0.4 over 0.6, which if you switch to fractions is 4 over 10 over 6 over 10, which is actually 4 over 6, which we could reduce to 2 over 3. So the odds in favor of E are 2 to 3. So in 5 trials, we would expect it to occur 2 times and not occur 3 times. Okay, so that is sort of the harder one, I think. So that's some basic probability.